Welcome everyone. My name is fergal.white and I'm an architect and a certified Passivhaus designer, and I work with Pidcock Architecture and Sustainability in Sydney. We would like to think of this workshop as a continuation from the Passivhaus in a Nutshell talk given by Darren O'Dea of the Australian Passivhaus Association earlier. I will be talking for the first half hour before handing over to another Passivhaus architect, Kylie Mills, who will cover another set of topics for the second. Here is a quick overview of the talk. It is quite a lot for 30 minutes, but please note I will make all slides and information available after the talk, so there is no need to take notes. Okay then, from the top, I will quickly do a recap of the importance of energy efficiency and how domestic energy efficiency is delivered in Australia at the moment. But my main topic will be looking at an example of a certified passive house in Canberra and seeing what adjustments need to be made to this house for it to satisfy the passive house standard in Sydney. I'll finish off with a summary of a pathway to passive house in the Sydney climate based on this study. Okay, so let's do a quick recap on what exactly the Passive House standard is and why I think it has an importance at both a local and a global level. So what is the Passive House standard exactly? The Passive House standard is a rigorous and climate-specific international building standard for energy efficiency and health and comfort. So what exactly does this mean? This means that the Passive House standard is a proven strategy for delivering very comfortable and healthy buildings which require minimal energy to run, and it works at any location in the world. Energy efficiency, of course, works on both the local and global level, but let's just focus on the local level. The Passive House standard delivers energy savings of up to 90% on standard building stock and 75% on code compliant new constructions. From a global perspective, it is good to remind ourselves of how much of the world's electricity is consumed by buildings and what that means in terms of carbon and climate change. The key takeaway here is that buildings use about 40% of global energy and they emit approximately a third of greenhouse gas emissions. So what are we talking about in relation to health and comfort? So with thermal comfort, this is all areas of the house at 20 degrees with controlled humidity all year round, with a maximum of 25 degrees in summer. And this is a consistency of temperature, so there's no cold spots within the house, no cold spots in walls, at windows or anything like that. With a healthy indoor environment, we're talking about all year round fresh filtered air to all areas of the house, and this is not recycled air like you would have with an air conditioning system. So let's look at how domestic energy efficiency is currently delivered worldwide and in Australia, and where Passivhaus sits in relation to all this. In general, there are two ways for governments to deliver energy efficient homes: setting examples of construction that is deemed to satisfy, or requiring homes to use a specified home energy rating scheme and achieve a certain standard with that scheme. This slide shows a building code typical deemed to satisfy illustration and a range of international home energy rating schemes, of which Passivhaus is one. So how is domestic energy efficiency delivered in Australia? Australia requires all new houses to be thermally modelled using the nationwide house energy rating scheme and to reach specified star ratings depending on which part of Australia you are in. For Australia in general, it is required that your new house be designed in such a way that the amount of heating and cooling energy required is no higher than a 6-star NatHERS star rating. So what does a 6-star NatHERS rating equate to? Well, it depends on where your new house is located. NatHERS splits Australia into 69 different climate zones, and the amount of heating or cooling energy that is required to satisfy that 6-star target can differ greatly. The requirement for 6 stars has been relaxed in both the Northern Territory and New South Wales for various reasons. So you can see the amount of energy allowed for heating and cooling in a new house can vary greatly depending on where this house is located, by up to a factor of 6. So how does this relate to Passivhaus? I would like to show you a quick comparison between NatHERS and Passivhaus, which is based on a study completed by the Australian Passivhaus Association. Design for Place is an Australian government initiative which provides free 7-star sustainable energy efficient housing designs that are free to download. A single-story 3-bedroom option was taken and compared with a version of the design that was upgraded to the Passivhaus standard. This comparison was completed in the Sydney Mascot climate zone, which is shown here in green on the map. Keep in mind that a 4 to 5-star house will satisfy building code in New South Wales. The result shows that this 3-bedroom house design will use 82% less energy and be 30% less likely to allow internal temperatures to drift higher than 25 degrees without mechanical cooling if it is built to the Passivhaus standard rather than the NatHERS 7-star standard. So let's take a look at a similar house design which has actually been built as a certified Passivhaus. Whilst there are a number of local projects underway, there are currently no certified Passivhouses in Sydney. Okay, so let's take a look at a built example of a certified Passivhaus in Australia. This is a Passivhaus which was built in Canberra, the city with the lowest average minimum temperature in Australia. This is the house of certified Passivhaus designer Hardy Truong, a remarkable individual who not only built 2 of the first certified Passivhouses in Australia, he also made publicly available all his design and certification documentation. A very generous gesture. Let's take a quick look at the Canberra climate in relation to the Sydney climate, which we all know. Here we have mean maximum and mean minimum temperature comparisons, with the internal Passivhaus comfort range highlighted. The takeaway here is that it is a greater challenge to achieve the Passivhaus standard in the Canberra climate, as Sydney's temperatures are always closer to the desired internal temperature range. You would therefore expect a theoretical Sydney Passivhaus to require a less insulated envelope. So here is Hardy's house, which I visited on the coldest day of the year in 2015 when I travelled down to interview him for a magazine article. The project actually comprises of 2 Passivhouses located on a corner site in suburban Canberra. We will be using the more northerly house of the 2 as our reference building. Hardy's Passivhaus has a classic passive solar design plan layout, with all living areas to the north facing the sun and all serviced areas to the south. It is a single-storey 3-bedroom house with a treated floor area of 127 metres squared. To maximise winter passive heating, the majority of glazing is located to these north-facing living areas. There are a small number of windows to the south and 1 tiny west window. Whilst there is a northern roof overhang, shading is provided to each window by means of a retractable external shade. Sectionally, the house is serviced by 2 bulkheads running east-west along both north and south external walls. And this arrangement facilitates the heating and ventilation for the house, which has fresh air supplied through the northern bulkhead and extracted through the outlets in the southern bulkhead. The corridor area becomes a transferred air zone where the supplied fresh air is pulled through door vents across the corridor to be extracted by the southern bulkhead from within the various serviced rooms. And here is a photo of the living, dining, kitchen area. You can see the large expanse of glazing to the north and the smaller windows located on the south to enhance cross ventilation. Hardy uses an insulated concrete slab with a dark tile finish as thermal mass, which can absorb heat during the day and either use during winter or flush out with a natural ventilation during summer. So let's look in detail at 2 very important aspects of the Passivhaus standard: thermal bridge free construction and airtight construction. First up is thermal bridge free construction, and we will start at foundation level and work our way up. A thermal bridge is an area of the building envelope which is significantly higher heat transfer than surrounding materials, resulting in an overall reduction in thermal insulation values. It is when your insulation is bypassed by a very conductive material, allowing heat to be transferred through a wall or floor. In the images here we can see the thermal bridge that occurs along a ground floor slab edge when not properly insulated. An important aim of the Passivhaus construction is to minimize thermal bridges like these. Now, let's take a look at the construction detail at ground floor slab level. The external walls comprise of SIPs, or structural insulated panels, which sit on a continuous concrete footing which is thermally isolated from the ground floor slab by 100 mm of rigid insulation. As you can see, the ground floor slab edge is also thermally isolated from the exterior by the insulated SIP panel, and from the ground itself by 150 mm of rigid insulation. The red line is indicative of the airtight layer, which we'll discuss later, but comprises of the ground floor slab itself and Intello airtight membrane on the walls, joined by a tape at skirting level. We can now see the resulting insulation values for the various aspects of the construction, and also the isotherm image, which shows a clear thermal separation of outside from inside with no thermal bridge occurring. Now, let's take a look at construction on site. Here we see the concrete footings being poured. Now we also see the intermediate concrete ground beams, which are also separated by insulation from the ground floor slab. Here we have the SIP panels being assembled on site. These are all pre-cut in the factory to suit the particular design, so site work is minimized. It is essentially like putting a jigsaw together. Harley decided on using SIP panels for their high insulative values and ease of construction. Here we see the SIP bottom plate sitting on the waterproof membrane on top of the footing. A SIP panel has minimal timber structural members that bridge across the wall structure in comparison with, say, traditional timber frame wall construction. Now all external walls and roof are in place, and we can clearly see all concrete footings and ground beams. We can also see all services and waste outlets that will be penetrating the slab. These will all require to have airtight tape sealing them to the top of the ground floor slab as part of the airtight layer. We will discuss this and the roof later on. Now we see the underslab insulation installed. This is a complete layer of insulation covering all ground, footings and ground beams. Now we see the ground floor slab being poured. Because the ground floor slab is not actually connected to the footings, it meant that the envelope could be in place and then the ground floor slab and insulation installed inside under shelter. And finally we see the contractors allowing for the bathroom floor and its slope finishes to drains. Okay, now let's focus on the construction detail where the roof meets the external wall and how thermal bridges are avoided here. The roof comprises of a 200 mm insulated steel roof sandwich panel, which spans, self-supporting, onto the top of the SIP panels of the external wall. The clear advantage here is that there are no structural roof members required, so there is a complete, uninterrupted layer of insulation between inside and outside at roof level. However, the underside of the roof panel is also a steel sheet, and this steel face spans between inside and outside, causing a thermal bridge. This thermal bridge is removed by the builder, who cuts a thermal cut across the panel with a saw blade, so that the underside surface of the panel is not continuous. You can see how this works in the isotherm image here. The builder then locates a holding screw either side of this thermal cut. Here we have an image of the builder putting in place the thermal cut on the underside face of each roof panel. Here is a detail shot of the typical thermal cut, which is approximately 3 mm wide. Once the external prefabricated SIP wall panels are assembled on site, the roof panels are immediately lifted into place. No time is wasted putting roof structure in place, as is not required. Once lifted, the sheets are then maneuvered so that they click into place. The underside steel face of the roof panels will form the airtight layer. A special airtight tape will be used to cover all joints between panels. Harley couldn't find suitable Passivhaus certified windows at the time of the build and had to import double glazed PVC windows from Germany. Of course, suitable double glazed windows are now available in Australia. As with all junctions, the window wall junction is tested for thermal bridging. These windows are Passivhaus certified, so also form part of the airtight layer, when closed of course. So here we can see what the Passivhaus heating energy target is and how the Canberra house fared out. The heating energy targets can be met by either having a heating energy demand of 15 kilowatt hours per meter squared per annum or less, or to have a heating power load of 10 watts per meter squared or less on the coldest day. As the upper limit of 25 degrees internally is not exceeded in the Canberra house for more than 10% of the cooling season, this means that no mechanical cooling is required. Now we can take a look at some of the air tightness detailing. At window SIP panel junctions, firstly a polyurethane spray foam is used. These junctions are then carefully secured with a special air tightness adhesive tape. At this point, the main external wall air tightness membrane is brought into play, and all junctions are again taped with a special airtight adhesive tape. This ensures the air tightness layer runs from wall to window seamlessly. Now the air tightness membrane is used throughout, and all joints are taped, along with all joints between the roof sandwich panels above. Once the builder is confident that the house is airtight, he will set about doing a blower door test. Harley performed a number of blower door tests prior to the final one for certification to ensure that he made the Passivhaus target. Harley has said that sometimes just wetting the back of your hand and going around the junctions yourself is a good way of starting to test for airtightness. In the end, all of the preliminary testing paid off, and Harley's house actually surpassed the Passivhaus air tightness target of 0.6 air changes per hour at 50 Pascal by achieving a 0.1 air change per hour at 50 Pascal to deliver in fact the most airtight house in Australia. An important part of a certified Passivhaus is the ability to deliver fresh air to all the house all the time. Harley devised a simple but ingenious mechanical ventilation system. Fresh external air is brought in from the south and enters the heat exchange, where it takes all the heat from the exhausting air and heads over to the northern bulkhead, and it is dispersed throughout the house. This air is eventually extracted through extracts in the southern bulkhead, and any heat that's gained is handed over to incoming fresh air in the heat exchanger again, and the mechanical ventilation cycle goes on. Here we see a photo of the heat exchanger unit and a diagram of how it works. Here are some shots of the supply and extract bulkhead units. In the second half of this workshop, Collie Mills will be looking at mechanical ventilation in great detail. So let's now recap on the main points of interest in relation to the Canberra Passivhaus. So we have a treated floor area of 127 meters squared, 3-bedroom house, single story. Air changes, so the air tightness is greater than what the Passivhaus requirement is at 0.1 air changes per hour. Heating demand meets the target, heating load doesn't, but we only need the heating demand to meet it to pass. No mechanical cooling required because the overheating percentage is very low. No passive night ventilation required, although Harley does use it because it makes sense. And then we get our averages. We have a 3.5 R value for the wall, 4.9 for the floor and for the roof. So what does this all mean in reality, and how is the house performing? Well, as we all know, our summers seem to be getting hotter each year, so let's have a quick look at the house's performance since August of last year. Harley has been keeping extensive records of temperatures in all areas of the house. Here we see results from the temperature meter in the living area and how this sat in relation to the external temperatures. Keep in mind that this is a house with no mechanical cooling system and uses only the mechanical ventilation heat exchange for heating. You can see how the internal temperature has been maintained within the comfort band of 20 to 25 degrees for the vast majority of the time, with a few peaks over 25 during the consecutive 40-degree days last February. I think you agree this is a pretty good performance. Okay, so this is all well and good, but what does it mean for Sydney? So let's take this exact house and relocate it at a site in the suburb of Asquith in Sydney and see what adjustments can be made to its external envelope in order to arrive at a Sydney version of this Passivhaus. So let's do a quick climate comparison, this time looking at the actual site-specific Passivhaus certified climate data. It is clear that the Sydney Passivhaus should not require as high a performing thermal envelope, as it is at all times much closer to the desired internal comfort range than the Canberra house. There are, however, two amendments that I am going to introduce to the Sydney Passivhaus. The first one is a night ventilation strategy. This is an important aspect of the Passivhaus software, and it allows for a strategy of flushing the house and the ground floor slab thermal mass at night when suitable. The second amended element is exchanging the SIP panel external wall construction for a more traditional timber frame construction. This is a timber frame arrangement we have used extensively with projects in the office. It uses a rigid vapour and airtight board taped at joints on the internal side of the frame for an air and vapour barrier, polyester insulation within the frame, and a breather membrane on the external side of the frame. All other arrangements of the Canberra house remain as before, including orientation. So now we come to information overload. Don't worry, we'll walk through this slowly and I'll summarise the important takeaways. This is a table which records the various thermal modelling runs I did using the Passivhaus PHPP software when I was investigating the relocation of the Canberra house in the Sydney site. Again, a reminder that I will make all the information available at the end of the talk. So what are we looking at? On the left hand side are listed all the various Passivhaus targets. On the right hand side are listed exactly what these targets are numerically. And in between the two sides are the various thermal runs completed with a yes, no or failure mark at the bottom of each. Anywhere you see NV, this relates to a night ventilation strategy. So let's start on the left with the existing house in Canberra, and as we already know, it passes all targets without using night ventilation and gets a yes for passing the Passivhaus standard. The next thermal run to the right of this is headed Sydney, and this is literally taking the exact house, no change in relocating in Sydney. Instantly we can see that the frequency of overheating almost quadruples, and the frequency of high humidity goes from 0 to 38% of the time. There's no surprise that the Canberra house unchanged would not pass the Passivhaus standard in Sydney, even if a night ventilation strategy was used. The next thermal run is headed Sydney Timber Frame 1. So here is the run which I think is the most suitable for the Sydney version of the Passivhaus. Here I use the timber frame construction approach instead of SIP wall panels. I also remove all underslab insulation and achieve the Passivhaus air tightness target. I employ a night ventilation strategy to overcome the frequency of high humidity limit. So here we have a version of the Canberra house that utilises timber frame construction with the minimum insulation value that the deemed to satisfy requirements of the building code allow. No underslab insulation, and it can achieve the Passivhaus standard with ease. The last run is headed Sydney Timber Frame 2, and this is a follow-on from the previous run where I just explore how little insulation you can put into the external envelope and still pass the Passivhaus standard. As you can see, the insulation levels can actually drop well below the deemed to satisfy requirements of the building code and still pass the Passivhaus standard. So what does this say? Well, first and foremost, it says that high insulation values are not required for the Sydney version of this Passivhaus in order to pass the Passivhaus standard. So let's do a quick summary of the main important points about the Sydney version of this Passivhaus. So first and foremost, large reduction in insulation values from the Canberra house. No insulation required under slab, use of ground coupling. Standard timber frame construction, that's a big one. No SIP panels required. Passive night ventilation required. no mechanical cooling required, and no mechanical heating required. All heating takes place just using the heat recovery of the fresh air mechanical ventilation. So what are the most important points to take away here? For a well-designed passive house in Sydney, the most important design and construction aspect will be a draft-free building envelope that minimises convection heat loss in winter, or drafts, and convection heat gain in summer. Provide building code compliant insulation, block out all direct summer sunlight, and provide a night ventilation strategy. With all this said, the most frequent question that I have been asked is not about cost, but can I open my windows and doors when I want? So to quote one of the founders of Passivhaus, Dr. Wolfgang Feist, yes, of course you can, and if you begin to feel uncomfortable, please feel free to close them whenever you want also. As you know, Sydney is blessed with quite a large Goldilocks period, and it is possible for a passive house to operate comfortably on natural ventilation for a good part of the year. I will just finish up by saying that the last vital component of the passive house jigsaw, mechanical ventilation, will now be taken on by Kylie Mills, the next speaker. I'd just like to thank you all for your attention and time.